Today we are going to learn about handling outliers and k-means clustering. We will explore techniques for detecting and managing outliers to ensure reliable clustering results and enhance your data analysis skills.
Welcome to our discussion on handling outliers and k-means clustering. Outliers are data points that deviate significantly from other observations, and they can heavily influence the results of clustering algorithms like k-means. In this video, we'll explore how to detect and handle these outliers effectively, ensuring more accurate and reliable clustering results. By the end of this session, you'll be equipped with various strategies to manage outliers, enhancing your data integrity and analysis skills. Let's dive in.
Outliers have a significant impact on k-means clustering. Since the k-means algorithm works by minimizing the variance within each cluster, the presence of outliers can lead to skewed centroid calculations. This means that outliers can pull centroids away from the actual center of the data points, resulting in clusters that don't accurately represent the data. Furthermore, these distorted centroids can influence the formation of clusters, leading to erroneous groupings and impacting the overall clustering results. Addressing outliers is crucial to maintain the integrity of the data analysis. In k-means, outliers can cause centroids to shift towards them, which might create clusters that are not meaningful. Let's explore this with an example. Imagine a dataset where most data points are around a certain region, but a few outliers are far from the rest. These outliers can cause the centroids to move towards them, leading to larger, less accurate clusters. This distortion can mislead your analysis, making it essential to handle outliers effectively. By understanding the impact of outliers, we can appreciate the importance of managing them in the k-means clustering process.
Detecting outliers is the first step in handling them effectively. Several statistical methods can be utilized for this purpose. One common method is using Z-scores, which measure the number of standard deviations a data point is from the mean. A Z-score above a certain threshold, typically 3, can indicate an outlier. Another method is the interquartile range, IQR, which uses the range between the first and third quartiles to identify outliers. Points that lie outside 1.5 times the IQR are considered potential outliers. These methods are based on the assumption that the data follows a normal distribution, which may not always be the case. However, they provide a solid foundation for initial outlier detection. Understanding statistical thresholds is crucial in applying these techniques. For instance, in the case of Z-scores, you must choose an appropriate threshold that balances sensitivity and specificity. Similarly, for IQR, adjusting the multiplier can help capture different levels of outlier extremity. Applying these methods in practice involves calculating the necessary statistics for your dataset, identifying potential outliers, and deciding on the next steps. These statistical methods offer a quantifiable approach to detecting outliers, providing a basis for further analysis.
Preprocessing data is a vital step in minimizing the impact of outliers on k-means clustering. Effective preprocessing can significantly enhance the quality of your data, leading to more accurate clustering results. One key aspect of preprocessing is data cleaning, which involves removing or correcting inaccuracies in the dataset. This includes handling missing values, which can be replaced with mean, median, or mode values, or using more advanced imputation techniques. Another essential technique is normalization or standardization, which scales the data to a uniform range or distribution. Normalization scales the data to a range of 0, 1, while standardization scales it to have a mean of 0 and a standard deviation of 1. These techniques help in reducing the impact of outliers by ensuring that all features contribute equally to the distance calculations in k-means. Additionally, preprocessing may involve feature engineering, where new features are created or redundant features are eliminated to improve the dataset's quality. By investing time in preprocessing, you ensure that the data fed into the k-means algorithm is as clean and consistent as possible, reducing the risk of outliers skewing the results. This sets the foundation for more reliable and accurate clustering outcomes. Robust scaling techniques offer a more resistant approach to handling outliers compared to standard scaling methods. Unlike normalization or standardization, which can be influenced by extreme values, robust scaling uses measures of central tendency that are less affected by outliers, such as the median and the IQR. One popular method is the robust scaler, which scales the data according to the IQR. This means that the data points are scaled relative to the central 50% of the data, making it more robust to outliers. Robust scaling is particularly useful in datasets with skewed distributions, where traditional scaling might not be effective. By focusing on the central tendency and dispersion of the data, robust scaling ensures that outliers do not disproportionately affect the scaling process. This results in a more accurate representation of the data's intrinsic structure, leading to better clustering outcomes in k-means. When implementing k-means clustering, applying robust scaling can significantly improve the algorithm's performance by ensuring that the distance calculations are not heavily influenced by extreme values. This makes robust scaling a valuable tool in the preprocessing arsenal, particularly when dealing with datasets prone to outliers.
K-means++ is an advanced initialization technique designed to improve the clustering process and mitigate the influence of outliers. Unlike the standard random initialization in k-means, k-means++ selects initial centroids that are more spread out, aiming to avoid poor clustering results caused by unlucky centroid placement. This is achieved by choosing the first centroid randomly and then selecting subsequent centroids based on their distance from the already chosen centroids. By doing so, k-means++ reduces the chance of centroids being placed near outliers, which can skew the clustering results. The benefits of k-means++ include improved convergence speed and clustering accuracy. The technique ensures that the initial centroids are more representative of the data's distribution, leading to faster and more reliable convergence to the optimal clustering solution. Implementing k-means++ is straightforward and is often available as an option in many machine learning libraries, making it an accessible enhancement to the traditional k-means algorithm. By adopting k-means++, you can significantly reduce the susceptibility of your clustering results to outliers, leading to more accurate and meaningful groupings of your data.
DBSCAN, or density-based spatial clustering of applications with noise, is a powerful clustering algorithm that excels in identifying outliers. Unlike k-means, which is distance-based, DBSCAN focuses on the density of data points to form clusters. This makes it particularly effective in detecting noise points, which are considered outliers. DBSCAN works by identifying dense regions of data points and expanding clusters from these regions. Points that do not belong to any dense region are labeled as noise, effectively categorizing them as outliers. This density-based approach allows DBSCAN to handle datasets with varying cluster shapes and sizes, making it a versatile tool for outlier detection. One of the key advantages of DBSCAN is its ability to identify clusters without requiring a predefined number of clusters, unlike k-means. Integrating DBSCAN with k-means can enhance outlier detection and clustering accuracy. By first applying DBSCAN to identify and remove outliers, you can pre-process the data before running k-means, ensuring that the clustering process is not distorted by noise points. This combination leverages the strengths of both algorithms, leading to more robust and reliable clustering results.
Let's explore a practical case study on handling outliers in a sample dataset. We'll walk through the process of identifying and managing outliers to improve clustering results. Our sample dataset consists of customer data from a retail store, including features such as age, annual income, and spending score. The goal is to cluster customers into meaningful groups for targeted marketing. First, we'll identify potential outliers using statistical methods like Z-scores and IQR. This helps us detect customers whose spending behavior deviates significantly from the norm. Next, we'll pre-process the data by normalizing the features and applying robust scaling techniques to minimize the impact of outliers. This ensures a more consistent and reliable dataset for clustering. We then apply k-means++ for initialization, providing a solid starting point for the clustering process. By combining this with DBSCAN, we can identify and remove noise points, further enhancing the dataset's quality. Finally, we analyze the improved clustering results, observing more distinct and meaningful customer segments. This case study demonstrates the effectiveness of the strategies we've discussed, highlighting the benefits of proper outlier handling and k-means clustering. In this section, we'll demonstrate how to implement outlier processing in Python using popular libraries. We'll walk through the steps of detecting and handling outliers, preparing the data for k-means clustering. We'll start by importing essential libraries like NumPy, Pandas, scikit-learn, and matplotlib. These libraries provide the necessary tools for data manipulation, statistical analysis, and visualization. We'll load our sample dataset and begin by calculating Z-scores and IQR to identify potential outliers. This involves creating new columns in the data frame to store these metrics and using them to filter out extreme values. Next, we'll pre-process the data by applying normalization and robust scaling techniques. Using scikit-learn's preprocessing module, we'll scale the dataset to ensure consistency and reduce the impact of outliers. We then implement k-means++ from the scikit-learn library, setting the initialization parameter to k-means++ to leverage its benefits. To enhance our clustering process, we'll integrate DBSCAN to identify and remove noise points, ensuring a cleaner dataset for k-means. Finally, we'll visualize the clustering results using matplotlib, creating scatter plots to illustrate the distinct clusters and highlight the improvements achieved through effective outlier handling. This Python code demonstration provides a practical guide to implementing the techniques discussed, equipping you with the skills to manage outliers in your data analysis projects.
As we conclude our discussion on handling outliers in k-means clustering, let's reflect on the key takeaways. Outliers can significantly distort clustering results, making it crucial to address them effectively. We've explored various techniques and tools, from statistical methods for detection to robust pre-processing strategies. By implementing k-means++ initialization and integrating DBSCAN, you can enhance your clustering accuracy and achieve more reliable results. Remember, the key to successful data analysis lies in effectively managing outliers, ensuring data integrity, and leveraging the right techniques for your specific dataset. We encourage you to continue exploring these methods and apply them to your data projects, enhancing your analytical skills and achieving meaningful insights. Thank you for joining us, and we look forward to seeing how you apply these skills in your data journey.